Okay, cool. Thanks. Yeah, so I guess I should say, I'm gonna try. This is just an introductory lecture, so of course, if you have any questions, feel free to ask at any point, and stop me. So I guess I want to state the sort of main conjecture that that we're interested in proving, and it's the following. So let's let X be a smooth, and I guess I should say everything I'm talking about in this lecture is going to be over the complex numbers. So a smooth projective variety. F is a foliation. So I'll say that I'll do a sort of refresher on what foliations are. I know for a lot of people here this will be old hat, but I think there are enough new people here that it was worth spending time on what foliations are. So I'll do a refresher on what foliations are in a bit. So we have a smooth projective variety and a foliation with mild singularities. And I'll be more precise about what these singularities are in a little bit. And the conjecture says that, well, so given this data, there should exist there exists a KF negative. I'll define what this is. Birational contraction. We'll call it phi. Such that one of two things happens. Either one, so if we let f prime to be the transform of f, then kf prime is nef. So by this I mean that kf prime dotted with c is non-negative for all c inside x, all projective curves inside x, or there exists a contraction or a morphism f of x prime down to z such that minus kf prime is f ample. And I guess also in this case, and the leaves of f prime, or equivalently f, are covered by rational curves. Okay, so this is, and I guess we'll refer to this as the minimal model conjecture. Yes, exactly. Yeah. So yeah, I'm gonna make a big list of some extra remarks. Yeah. So yeah, that's a great question. Yeah. So in general, so even if we start with x smooth, in general, x prime will be singular. A priori, it's unclear what sort of singularities show up on x prime. So this is one thing that we have to work a bit on to control, or we think, control something about it. I guess maybe just to state it, this is an analog of the classical minimal model conjecture. And this is, of course, the sort of motivating reason for this. I guess, oh yeah, I never defined kf negative for you. So let me define kf negative. So kf negative, okay, so I'll write it maybe in a slightly strange way, but this turns out to be a good way of describing it. So if we let W resolve the indeterminacies of the rational map x prime, so P and Q, this means that pi star kf is equal to q star kf prime plus E, where E is effective. Okay, so it turns out that we can rephrase this in terms of some numerical condition on the canonical bundle of the foliations, what this kf is. But the important point, or I guess the most important aspect of this, is that being kf negative, this implies that the pluricanonical sections of kf are unchanged by the steps of the MMP. And this is somehow the most important aspect. This is why kf negativity is important. So somehow this is, these surgery operations are respecting some fundamental invariance of the foliation. Then, okay, so maybe remark 4, the KF MMP, so the KF minimal model program, because that's really what these talks are all about. This is an algorithm, is a conjectural algorithm for proving the minimal model conjecture. And what we'll talk, I guess what Paolo will talk about in the next couple lectures is how we run, what exactly the steps of this algorithm consist in. But just to maybe just to fix some notations, these are common words that are bandied about. Okay, then maybe the last comment I want to make, and this is for the people coming from an MMP background, is that the theory of foliations or the sort of the theory of the birational geometry of foliations and the birational geometry of varieties differ in some pretty important ways. So for instance, abundance is false for foliations. And maybe time permitting, I'll get into some of these examples. Yes.
What you mean by if you have minimal program is what you do, or is it some?
So yeah, it's a hidden. Yeah, we'll explain it. Yeah, so this is Paolo's job, or at least okay. I mean, Paolo, I think it's your job at least. Yeah. Okay. Yeah. Now it is. Sorry. Yeah. But yeah. So what? Yeah. So the idea is that yeah. So I mean, how would one prove such a conjecture? I mean, who knows? But the idea is that this is an algorithm. We have a conjectural algorithm for proving it exactly, and this is what we'll get into in the next couple lectures. Yeah. Yeah. Thanks. Things like KV vanishing, base point free theorem, etc., are also false. For foliations. So just to say that somehow these right here are some of the key tools in the classical MMP, but they don't work for foliation. So somehow we need to use other ideas. Okay. So I guess what I'll do next is I'll do a sort of crash course on foliations. What is a foliation? And of course, if anyone wants to add anything, they should feel free. Okay, so any other questions on sort of our objective for these talks so our objective for these talks is to say something about the minimal model conjecture for threefolds. And hopefully I'll be able to explain to you guys in a bit why threefolds are somehow the important case, or one of the important cases. Okay, so what's a foliation? So Okay, so for me, let's let X be a normal variety. So a foliation F is the data of a subsheaf, a coherent subsheaf, TF inside TX, such that two things hold. One, we need an integrability condition. So we need that this tangent sheaf of the foliation is closed in early bracket. So yes, exactly, yeah. Thank you. Yeah. And two, we need a saturatedness condition. So we need TX mod TF to be torsion free. So this last one, number two, is somehow a kind of like normality condition that we have. Okay, so so here's some very, I guess, simple-minded remarks. Sorry?
How essential is the normality assumption?
That's a good question. Maybe I don't want to say anything while I'm being recorded. I don't know if anyone has a good notion of what a foliation is on a non-normal variety. I have guesses. Okay, the answer is should be not super necessary, but finding the right way to state it maybe is a bit delicate. But yeah, maybe we should talk about this. I think that's a good thing to talk about, is what the good definition is. But yeah, so I guess, yeah, for right now everything will be normal. But yeah, that's a very good question. So the issue really is the sort of saturatedness condition. Okay, so the issue I have in mind, the issue I have in mind, or I guess the prototype, or one of the prototype concerns I have is the following. So let's look at, okay, so this is taking us a bit off field, but okay, so let's look at a resolution of a cusp in a Hilbert modular surface. So this is in, so resolution of a cusp on a Hilbert modular surface. The issue is basically comes down to a junction issue. That on one hand, we know that KF restricted to C, so we call this thing C, and I guess F is one of the tautological foliations. Okay, so we know that KF dotted with restricted to C is non-torsion. However, the foliation, so all these curves are invariant by the foliation. So KF dotted with C is non-torsion. So the question is, well, what's the correct notion of the restricted foliation to C? Well, sort of, on one hand, you might be tempted to think, well, somehow the natural notion is, well, it's like the tangent bundle of this nodal curve. But if you do that, then this is torsion. So you don't see the non-torsionness of the foliation restricted to C. So somehow a junction doesn't really quite work out if you think about these things naively. So in some sense, you want foliations on the nodal curve, which are not the tangent bundle of the curve. Or you want rank 1 foliations on the nodal curve, which are not the tangent bundle of the nodal curve. And this is the sort of thing that worries me. So I guess maybe I'll talk about a junction in a bit, but really the issue is what's the right setup for a junction for non-normal varieties, or for foliations on non-normal varieties. So actually, I'll explain some adjunction results in a bit, but I'll always go past the normalization. So this is what has me worried. Okay. Yeah, that's a good question though. I mean, but all I have is, so yeah. Okay. Where was I? Right. Okay, so here, I want to make a much more simple-minded a much more simple-minded observation. So, okay, so let's let U inside X be a Zariski open subset, and let F of U be a foliation on U. Then there exists a unique foliation F on X such that F restricted to U is just F of U. Okay, this is just that every subsheaf or every subsheaf of a coherent sheaf admits a unique extension. On U admits a unique extension to all of X. So in particular, if phi from X to X prime is birational, then there exists a well-defined and F is a foliation on X. Then there exists a well-defined strict transform foliation of F, which will denote phi lower star of F, which some maybe will call F prime. Okay, so in particular, when we run steps of this, when we were doing the MMP, there really is a well-defined transform of the foliation. Yes. Exactly. Yeah. This is exactly another part. Yeah. Exactly. And this is and essentially, it comes down to this. Like here, somehow it's a saturatedness issue. Really the problem is, you can't really make the on non-normal things. Arranging for number 2 to hold isn't really possible. It's not possible to do this. So you need to either you just drop it entirely, or you need to think of a more subtle way to do it. But yeah, exactly. So yeah, as Carlos was saying, yeah, this is somehow there are lots of things which go wrong for non-normal things. But so yeah, we have to be careful about the right setup of what a foliation is on a non-normal variety. Although it's important to have the right notion, though. This is certainly important. Okay, let's see here. So I guess another remark. There's a sort of a dual picture. I don't think we'll need this very much in anything we're talking about, either today or anywhere else. But it's just worth to bear in mind. So dually, we can think of a foliation can be defined as a subsheaf of omega 1x, and this is just the reflexive hull of omega 1x by looking at by taking the annihilator the annihilator of TF inside TX. So there's I guess there's sometimes it's more convenient to think about foliations being defined by vector fields. Sometimes it's more convenient to think of foliations being defined by one forms or a subsheaf of, yeah. So yeah, and I guess we'll normally call this the cotangent sheaf. Yeah, thank you. Conormal, yes, thank you. Yeah, conormal, yeah. Like I said, I don't think we'll need this description at any point, but if you go in the literature, of course, this is a very, very standard way of looking at these things. Okay. So another so probably, okay, so this is the most important invariant we'll talk about today, is the canonical class KF is just by definition, well, I guess it is any Weil divisor such that O of KF is equal to the determinant of TF dual. So this is, I mean, so when TF is equal to TX, we just get that KF is our usual canonical divisor. And so then there's one other characterization of a foliation, which is going to be important for us in a little bit. And these are Faf fields. So what we can do is we take TF inside TX, we dualize it, we get omega 1 x to TF dual, and then we take the Rth wedge power. So let's let the rank of TF be equal to R, and we'll also refer to this as the rank of F, which is sometimes also referred to as the dimension of F. And we get then a non-zero map to O of KF, and this is the Faf field associated to F. So I should say that maybe I'll just say, because it was asked, I guess one maybe reasonable candidate for foliations on non-normal varieties is it's somehow better to look at Faf fields on those varieties, and to think about foliations as being defined by Faf fields instead. But okay, so
can you retrieve the foliation from that data?
Yeah. I mean, okay, you have to put some integrability condition on this. I mean, so I guess maybe it's an exercise to the to the audience or to the reader that there's some you can redefine the you can reinterpret the integrability condition here in terms of Faf fields, and then you can recover the foliation. Yeah. Okay. So. Yeah, you can, I mean, because we always have a map. So I guess we always have a map. So we always have a map omega 1 x to I mean, the natural map. So yeah, if you wanted to, we could define, yeah, Faf Fields in terms of the Kähler differentials. The reason why I want to write it in with the reflexive differentials is I want to define what I mean by the singular locus of a foliation. And that works better with the reflexive differentials. So the definition, so Sing F, well, what we can do is we can take our Faf field and we can twist it. So what we get is we have a morphism, omega r x tensor O of minus kf. I mean, I guess we're double dualizing here, so we could have started with Kähler differentials at any point. So yeah, maybe, okay, maybe it's a bit of a, maybe reflexive differentials are a bit of a red herring, but I guess I think they're a bit easier. Maybe it's more clear this way. And we get a map into OX. And the singular locus, and so now we look at, maybe I'll call this twisted one, phi tilde. And the image of phi tilde is some ideal sheaf, I, Z, and we take Z, so we take Sing F to be Z, maybe with reduced structure, maybe not. I mean, generally, all I care for right now is just what the points of the singular locus are, not any additional scheme structure on them, although there is an additional scheme structure. Okay, so this is how I define the singular locus of the foliation. So the reason why I've done it this way is because it works better. This is somehow the right definition for normal varieties. On a smooth variety, we have another, there's an equivalent characterization of the singular locus of F. So when X is smooth, well, we have the singular locus of F is the locus where TF fails, or TX mod TF is not locally free. Of course, when X is singular, this isn't such a good definition, but when X is smooth, you can see that these two definitions are equivalent. Okay. No, yeah, so okay, maybe, yeah, so I'll give an example. So let's look at C2 together with partial X. And then let's quotient this by a ZM action. So this is just, I don't know, zeta dotted with XY is zeta dotted with X, you know. So some MAB action, whatever MAB action. Okay, so and let's call this XF. Now the important point is that in this case, Sing X is equal to, you know, the origin, but Sing F is empty. And so the reason why this is a good definition, yeah, so the reason why I want to use this definition is that this somehow accurately detects that, okay, in an orbifold sense, this is a smoothly foliated point. And so we should consider this to really be a smooth foliation point, even though the underlying variety is singular. Another, I guess, another example is let's let X, oh, sorry. Because, so I guess if we just do the reason is that we can define this map. If we define this map on C2, it's equivariant with respect to the action. So this map then descends down to X, and it's still surjective down on the quotient. So yeah, and it just comes from the fact that we're twisting by the canonical class of the foliation. Yeah, good question. Actually, it's a general fact that if you have a smooth foliation on a smooth variety, and you quotient it by any group action, and assuming the foliation is equivariant with respect to the group action, the quotient of a smooth foliation will stay a smooth foliation in this sense for exactly that same reason. Yeah.
Does it make sense to define leaves outside of the single locus of the foliation?
Yeah, that's a good question. Yeah, so okay, I will say that. So I'll define leaf in a little bit here. I will say that for me, leaves will always be contained in the smooth locus of the variety. But I suppose if you're careful, you can define it in the singular locus. But so yeah, like there is. So in this case, if you have any leaf of this foliation, there's a unique extension of this as a subvariety of X, which is invariant underneath the foliation, et cetera, yeah. So there's, yeah, so somehow, yeah, you always have uniqueness, I guess, in these cases, but I guess maybe just to not abuse the previous literature on the subject too much, it's a good idea. I'll try and always keep my leaves in the smooth locus of the variety, but I think you're absolutely right that you have a bit more flexibility. Yeah, good question, thank you. Okay. What time is it actually?
35.
Oh, okay. Oh, okay. Well, so maybe okay. Maybe I won't give this example, but it's just another example where we see that the singular locus of X and the singular locus of F are not the same thing. Okay. Invariance. So, and this ties back to Yarek's question about leaves. Somehow, a better notion of leaf, or in the singular case, is the notion of invariant variety of invariance. This is somehow a better notion. So we say a variety W inside X is F invariant, provided for all local sections of the tangent bundle or the tangent sheaf, we have that the ideal sheaf is invariant underneath derivation. Okay. Okay. And now, because I'd be remiss to give, say anything about foliations without the Frobenius theorem. So suppose X is smooth, and F is smooth, or maybe, and Sing F is empty. So we have a smooth foliation on a smooth variety. Then for all X in X, there exists a Euclidean neighborhood U of X and a holomorphic submersion call it F from U to V, such that TF restricted to U is just the kernel of DF, or equivalently, it's the relative tangent bundle of TUV. So all this is saying, so the interpretation of this, all this is saying is that so if you have some variety X and a smooth foliation, and you fix any point, in any small neighborhood of a point, the foliation is just given by a fibration. Of course, so locally, F is a fibration. So analytic locally, F is a fibration. But the warning is, globally, this isn't true. And so I think there is some, so globally, you could have something, you could have some, okay, I mean, this, you could have some crazy transcendental orbit of the foliation. And so maybe I'll find a leaf of F is a maximal a maximal immersion iota from L into X minus the singular locus of X union with the singular locus of F. So I want my leaves to be disjoint from the singular locus of X and F, such that the dimension of L is the dimension of F, and such that di of TL is contained inside TF. So it integrates the differential equations. And so another way of saying this is that in general, leaves are transcendental. So leaves are transcendental. Okay. Okay, so this is somehow a crash course in foliations. So I want to talk, or I guess I won't prove anything, but I'll say that this is somehow a sort of fundamental idea in birational geometry. I guess just in geometry, period. And we can do it for foliations. So I want to talk about a junction. And the idea is that a good way to study a foliation is to restrict a foliation to divisors. Not algebraic. So yeah, that's a good definition of that. Sorry? So what I want to do is I don't want to take this to be my leaf. You know, it emits some analytic continuation. So the maximal analytic continuation of a local leaf. Yeah. Okay. So the setup for a junction is the following. So what we want to take is X, F, and then a pair delta. So this is our normal variety. This is a foliation, and delta is a Q Vey divisor. If you want, you can think it's a Vey divisor, not a big deal. And what I want is I want delta to be equal to epsilon S plus delta prime, where S and delta prime have distinct supports, and epsilon S is equal to 0 if S is invariant, and 1 otherwise. Yeah.
For Venn theorem, usually foliation induces vibration, right?
Locally, they induce a vibration. Yeah.
But globally, it's net. Vibration net.
No.
The leaves can be dense. It's just really local.
Okay.
Yeah, so yeah, maybe the example to think about, I guess always the classic example is look at consider C2 mod a lattice. So this is some abelian variety. And then think about the foliation on C2, just given by parallel lines. And then this is going to induce on the torus a foliation on the torus. But depending on, I mean, for a general choice of the slope of these lines, the image of all these copies of C is going to be dense inside this torus. And that gives a totally reasonable foliation, which of course locally is given by a fibration, because, but yeah, globally, as George says, the leaves are dense. Yeah, so yeah, good question, but yeah, definitely globally the geometry of the foliation could be very, very complicated. Yeah, thanks. Okay, yeah, so this is our junction setup. Now, the junction comes in, has two parts. The first part is that there exists a canonically defined restriction. Restriction foliation Fs. So there's a canonical way to restrict the foliation to S. And moreover, there's a canonically defined different delta S. Oh yeah, thanks. Yeah, exactly. Yeah, thank you. Yeah, S and yeah, thank you. Yeah, S for me here is an irreducible, yeah, prime V divisor with coefficient 0 or 1. Yeah, so S is irreducible. Yeah. And yeah, as George says, yeah, it's just on the normalization because of the issues we were mentioning earlier about what's a foliation on a non-normal variety. And so there exists a canonically defined restricted foliation and a canonically defined different, such that n star kf plus delta is Q-linear equivalent to kf Sn plus delta Sn. So this is exactly the analog of the classical adjunction formula. Yeah, so yeah, and yeah, so delta, yeah, and I guess maybe S is not contained in the support of delta prime. Yeah, thank you. And I guess maybe I should also mention that the different is always effective as well. Yeah, I still think Keeler, yeah, but exactly, yeah, even for KX, yeah. So I guess, yeah, I'm thinking, I mean, because you could imagine like you have some like, cyclic quotient singularities in codimension 2 or something like this. This is the sort of thing that messes up. Yeah, so yeah, I guess I should say that, yeah, and here kf plus delta is Q Cartier. Actually, that's not essential. I mean, because it's a codimension 2 phenomenon. So as long as it's Q Cartier in codimension 2, that's good enough. Oh yeah, you're right. Yeah, delta is effective. Yeah. So whenever thanks. Yeah. So whenever I write delta, my deltas are always effective. My kf plus deltas basically are always Q Cartier. Yeah. No, this is the important thing. Yeah, I'm not asking anything about kx or kx plus delta, nothing. Yeah, this is an important point. I mean, of course, a posteriori, it turns out that in all the cases we care about, kx plus delta will be KLT. So a posteriori, I mean, it's kx plus delta is Q Cartier. But that's just sort of, that's a non-trivial consequence, but yeah.
Is the construction some Poincare residue map?
Exactly, it's a residue thing. Yeah, exactly. I mean, so yeah, so maybe I want to say is that, yeah, when epsilon of S is equal to 1. So this is so when epsilon of S is equal to 1, this is somehow the classical case. We have S strung up with coefficient 1, and we have a we have a Poincare residue type thing. Well, when epsilon of S is equal to 0, we have to do something a bit different. So what you observe is that, so let's just assume, so just to give a sketch of how this construction works, let's just assume that KF is Cartier. Let's assume KF is Cartier. And what we want to look at is we want to look at the Faf field associated to our foliation and restrict it to S. And so invariance actually tells us that we have a factorization like this. And now it's a result of, so now by, I guess, Seidenberg did one case, and then also Carolina and Stéphane Drouel. Oh, like, okay. Oh, and so this is okay. Oh, it's in the alphabetical order. That's even better. Thanks. Yeah. So yeah, what this turns out, actually, you can lift Faf fields to the normalization, and so this gives us a map. KF, or sorry, KF. Of course, the point is that this map is not surjective in codimension 1. And so delta S is the locus where, so delta S is the locus, or is the co-support of this map, because it might fail to be, again, it might fail to be surjective in codimension 1, and so that's where we get our different from. Yeah, divisorial part. Yeah. Yeah. Thanks. Okay. So I'll say that this Poincare residue thing, there are a few subtleties to it too, I should say. It's not exactly like in the classical junction formula, but it's not too different. Okay, so I guess the very important special case, okay. So so important special case. So this was stated for divisors. Actually, when the fact that it's a divisor isn't absolutely essential here. So so if V inside X is generically a leaf, is I guess is a subvariety which is generically a leaf, then we can still write, we still have KF equals K V plus delta Vn, where N Vn to V is the normalization. In general, I mean, you'd expect this to be, you'd expect a statement for any log canonical center, whatever that means. But it just so happens that varieties which are generically leaves are always log canonical centers. Okay, so I guess one thing, okay, so I was planning on defining the classes of singularities of the MMP, but I guess I won't do that because I want to talk about something else. This is somehow a really delicate part of the story, and it turns out to be very important for us. So it's understanding suppositories of foliations. This is very delicate, actually, I think. So let's let X be a smooth variety. And let's let F be a foliation. Of course, smoothness here is not essential, but of course we'll have to drop it later, but that's not so important for right now. F is a foliation, and C inside X is a curve, which is tangent to F. So by this, I mean generically, C is contained in a leaf. Okay. So we have the following extension problem. Okay. Does there exist a neighborhood U of C? So this is a Euclidean neighborhood. And an analytic subvariety V, so our analytic subvariety is V, such that V is generically a leaf. Okay, and maybe I guess I'll just say in words. I'm being a bit loose here. We also sometimes want to consider curves in the singular locus of the foliation, but we'll leave that aside for the moment. So the question is, yeah, does there? So if we're given a curve C, tangent to the foliation,
So your curves also negative.
my curves will always be, well, okay. I guess yeah. The setup right now is analytic. I guess I'll really want to focus on the case of a projective curve in the end. That's all I really care about is projective curves. But so the extension problem is like, if you have this trajectory tangent to the foliation, can you extend it to a full solution of the foliation? So maybe I'll just so so I guess the picture is this: here we have our curve C, and then maybe at some point of the curve we have this green thing, and this is a germ of a leaf. And the extension problem asks, can you extend this germ of a leaf to something containing the entire curve C? Okay, now this is a really delicate problem. So before I go on, I'll say that I'll just make a remark, is when the rank of F is equal to 1, this is easy because C itself was already a leaf. So there's nothing to do here in this case. This case is easy. When F is smooth, this is just Frobenius, basically. The difficulty is when you have a singularity of the foliation. So this is the hard part, is let's say you have a singularity here. Frobenius, if you follow Frobenius, what you see is you start gluing together germs of leaves, but somehow the radius of convergence of the leaves a priori gets smaller and smaller and smaller. And so you have this delicate question of, can you extend this solution across the singular locus? So, so the hard case is when F is singular. It's trivial in the rank 1 case just because C is a curve which is generically contained inside a leaf, and every leaf is one-dimensional, and so yeah, sorry, yeah, exactly. It's just stupid by dimension reasons. Yeah.
It's not easy.
It's not easy. Okay. It's empty. Yeah. Yeah. I mean, yeah, I don't want to say that because I always like to build myself up. I like to feel like I've done something every day. And so, if I could prove a theorem for a rank 1 foliation, then I feel pretty good. So yeah, the hard case, and I guess it's not the hard case, it's like the only case, I guess, by George's, well, okay, the smooth case is easy, but so the hard case is when F is singular. Okay.
Sorry, yeah. Why the smooth case is similar when you have a projective curve?
I mean, at every point, I guess the point is that, so let's say, I mean, at every point you have a unique leaf, right? Because F is smooth, and so these two things have to agree on overlaps, yeah. Okay, so yeah, the hard case is when F is singular. Okay, so here's a theorem. And so this is a theorem by Felipe Cano and Dominique Serveau.
So since C is contained in a leaf,
Yes.
what do you actually want to take other than the leaf?
Generic and spontaneous.
Yeah. So
there can be similar points of F on C.
So how is the second case non-empty again?
Well, I mean, it's not empty because Frobenius theorem is a non-empty theorem.
What we've done before, right?
Exactly. Yeah. Exactly. Exactly. Yeah. I mean, somehow, yeah. This is essentially it. Yeah.
So definitely, well, but the existence of leaves is used in the definition. So.
Yeah. Exactly. So somehow, yeah. I mean, in this, I mean, yeah. It's maybe in this case, yeah. I mean, if existence and uniqueness is, yeah. I mean, yeah. Exactly. Yeah. So maybe it is also empty. I don't know. I mean, I'd like to give Frobenius as much credit as possible, maybe. So.
What is our aim?
So our aim is, so the extension problem asks, so if we have, so okay, yeah, maybe I want to zoom in on a singular point. So here we have a curve tangent to the foliation, and here's a singular point. Who knows what it looks like? Now I know that at any point away from the singular locus, there exists a germ of a leaf. And so I know that somehow we have some picture like this. Like we have all these leaves, we can keep patching together leaves away from the singular locus. But I want something much stronger. I want actually some invariant variety. So it's not a leaf because it passes to the singular locus. But I want an invariant, I want a subvariety of an analytic neighborhood of the curve, of the whole curve, such that away from the singular locus, this analytic variety is a leaf. Of course, if I were just to take the union of all of these little leaves here, that's not going to be an analytic subvariety of an open neighborhood of the curve, just because, I mean, here what's going on. So yeah, it's really what you're trying to do is you're really trying to push the solution across the singular locus of the foliation. I mean, maybe another way of saying it is that at the singular locus of the foliation, does there exist a solution to the system of differential equations defining the foliation? So it's another existence of solutions to systems of differential equations type statement, given some initial value data given by these leaves. So yeah, the crucial point is, yeah, like a priori at the singular locus, we don't know what's happening. And again, and I guess I should say that in general, so maybe, okay, before I state the Canonical theorem, I want to remark that in general, the extension problem has a negative answer. In general, it's not possible to do this. In general, you can have singularities which are so bad that you can't push through them. Even formally, yeah. So yeah, the Zhuang-Liu example. So if you look at a cone over the Zhuang-Liu foliation on P2 with no algebraic leaves, then yeah, exactly. There you don't, I mean, yeah, so that's true, yeah. So. Okay, yeah, so you compactify and then, yeah. Oh, but I mean, if we take a cone over the Zhuangnu example, this is an A1 over, this is a P, this is an A3 that we have here. And then we have lots of A1s passing through the origin.
But all these are contained in if you ask them to be tangent to the foliation, their points must be contained in the singular set.
Not if we take this to be, I mean, so here we have the Zhuangnu foliation on P2. We take we look at O of the tautological bundle on P2, O-1. We pull it back. We have a co-rank 1 foliation. And then we look at one of these things. This is an A1 not contained in the singular locus. Yeah. So yeah, maybe if we want to keep talking about it, yeah. So maybe after I finish here, I can give you the exact example showing that the extension problem has a negative answer. It's a very, very beautiful example. Actually, there are somehow lots of examples around this, but yeah. And as Fred asks, yeah, even formally locally. And of course, doing this formally is also an important aspect, which I'm sort of sweeping under the rug. Okay, so now there's this wonderful result of Cano and Cerveau, which I'll state in two ways. So let X be a threefold. And this is not the best possible statement. X is a threefold. Now, if F has non-dicritical singularities, and I guess I should say, well, let's say the rank, I mean, as we know, the rank F equal to 1 case is empty. So we really care about the rank of F equal to 2 case. So if F has non-dicritical singularities, then the extension problem has a positive answer. So you can always do this extension. I won't define what non-dicritical is, but I will say that somehow this very same result gives us, if F has canonical singularities. And this is a class of singularities coming from the MMP. And so this is one of the important features about canonical singularities, is that this extension property holds for canonical singularities. And somehow you can show that canonical implies non-dicritical. I don't know actually. Yeah, so definitely for co-rank 1, this is okay. Definitely when X is smooth, it's okay. If X is singular in higher dimensions and we have higher codimension varieties, it's very unclear to me. Yeah, so that's actually, I mean, so maybe, well, I guess maybe either later on we'll talk about, yeah, the comparisons between classes of MMP singularities and other notions. But yeah, I think that's a good question. I don't really know. Yeah, so definitely in dimension 3, this is true. When X is smooth, definitely canonical, and co-rank 1 implies non-dicritical in all dimensions. That's a pretty easy calculation, actually. But when you look at higher co-rank foliations, it's less clear to me what's happening. I mean, I guess canonical always implies non-dicritical for any appropriate definitions of these terms, but I don't know how to prove it. If you knew the MMP, the MMP implies that canonical implies non-dicritical. I guess I should say that. So yeah, so if you knew the MMP, then you'd have this statement. But and so then what I want to say then, this will be the last thing I say, is that, well, I'll say out loud, the proof of this uses resolution of singularities of foliations. And resolution of singularities for foliations is only known in dimension 3. And so, of course, there are somehow tricks to prove a statement like this in higher dimensions. So, but you can drop threefold. You can, so maybe I want to say co-rank. Maybe I want to say co-rank 1. You can drop the threefold hypothesis here in this statement if you want.
But then you have to put Matei names.
Yeah, I have to put more and more names. Exactly. Yeah. So yeah, Matei Musu. Well, Matei. Oh, it's Matei Kana. Yeah, you're right. Yeah. So yeah. Yeah. So maybe I'll just say it out loud. And there's also the delicacy about their stuff doesn't work for formal in the formal case, and we really want to do a formal extension too. And so I should say that in this Canonical and Cerveau paper, what they prove works in for formal invariant divisors as well. But in general, I don't know what one can say about the formal extension problem. And that's another good question: is how can you do the formal extension problem? Okay, so maybe I'll end there so we can drink lots of coffee. But yeah, okay, yeah, thanks.
Questions?
Just a remark, the line that Andrea was pointing to. It seems to be, if not easy, quite approachable, the rational extension problem, right? Because the real difficulty, if you allow to blow up, I think you can always extend. That should be something that people should look at. If it's not trivial. I'm afraid it's probably trivial.
No, but if you blow up, I mean, if you have a curve, oh no, so you're saying, yeah, no, it's a.
But perhaps try to push to see how much you can.
In the covering, I mean, this paper by Kano's student, what's his, Fernando Duke, this local resolution statement they have, would, I mean.
Oh, it's something like that. Yeah.
Yeah.
Yes, subtler than this.
Yeah.
In the extension problem, the curve C is automatically smooth, right?
No. I mean, it's not a big deal to take it to be smooth, but I mean, because in principle you could have, yeah, I mean, there's no reason you couldn't have like a cusp at the singular point here. There's no, I mean, somehow that's not a big deal. But yeah, I mean, C is not smooth here, but it's not a big deal to assume. Yeah.
Okay. Now let's thank Calum again, and then we resume after that.
Should I stop or pause the recording? Does it make a difference?
I would say stop, so that there are different videos, unless Fabio objects.
Stop.